Hi, Joan. Thank you, everyone, for coming. And everyone knows Dr. Bay, I assume. Yeah. So thank you for coming, Dr. Bay. We're going to try to do building blocks of analysis this year, more basics, so we can get you all comfortable with numbers somewhat.
Okay. Thank you for coming. And I know we have some people in Kirksville and elsewhere. So welcome. I just, before the microphone came on, I just asked partially in jest, what would you like to talk about? And I'm assuming blank slate, sort of, that most people don't know a lot about statistics. Okay, I've got everything in here from means and modes and medians to Cox proportional hazards, in case you want to talk about that. But we'll start at the beginning. And please, if you have any questions, break in, because otherwise talking about statistics is not the most exciting of subjects. Well, some people like statistics. So I was tasked with providing an introduction to statistics, which is a relatively vast area of knowledge and practice. We aren't going to get into theoretical statistics, but we will talk about the notions of measurement, a survey of basic descriptive statistics. What I really would like to talk about, or I think of that, which will be of most value, is inferential statistics and the logic underlying inferential tests, p-values, confidence intervals, and such. Because that's something that a lot of people don't grasp. And then if we have some time, we could go beyond that. I've been asked to give several talks recently, introductory talks about one to the KCOM third-year rotators and one to the second-year dental students. So I selected things that I call foundational analyses, which they will see commonly in the literature they're going to review for their, they have a critical review component of their coursework. So that ranges from basic statistics, descriptive statistics, to Cox proportional hazards, which are becoming, they're just popping up everywhere. So you kind of have to understand those in order to interpret pretty much any article from the New England Journal of Medicine or JAMA anymore. But we'll start with the notion of measurement, which is simply the act of assigning a number to a construct, a property. And that allows us to standardize a property and to measure and then to compare that property expressed as a number or a numeral across persons, places, and times. And statistics itself is the act of collecting, organizing, analyzing, and interpreting the data set that you collect through measurement. And the first thing you have to understand is that different types of measurement differ in terms of their precision. It depends on the construct you're measuring. So the smartest of all of those metrics is the interval ratio scales, where numbers represent units with equal intervals. And I typically combine those two when I'm talking about them because we don't distinguish that much between the two in statistics, but they do differ slightly, and I'll show you how that is. So we have interval/ratio, we have ordinal statistics, and then we have nominal statistics. Or maybe I should call them data, nominal data. So continuous statistics, like I said, the underlying most important property or characteristic of continuous data are that the intervals between units of measurements are identical, which allows us to add, subtract, multiply, and divide them. Age, weight, blood pressure are all measured on a continuum. Typically, we express those at least conventionally, we will express them as whole numbers because it's not important to know the units within the whole numbers. Blood pressure, it's 125/90. But we have the means, we have the instruments that could measure that to 6 or 7 decimal places precisely, but it's not really useful unless it's a research study where you're interested in the minutia. So ratio scales have equal intervals, but they have a true zero. Interval scales do not stop at 0. Temperature Fahrenheit is an interval measurement scale because it has an arbitrary 0. 0 means nothing. It just means 0. Kelvin temperature, 0 is the absolute lowest you can go. You can't have a negative Kelvin temperature. 0 is the absence of movement. So that's the distinction between the two. But we use them interchangeably for purposes of statistical analysis and presentation. Then we have ordinal data, which are simply rank-ordered data. The intervals between the units are not equal. Stage of cancer, 0 is the absence of invasion. Stage 4 is the cancer has metastasized. The distance between stage 1 and 2 is not the same as the distance between stage 3 and 4. Therefore, it makes no sense to add, subtract, multiply, and divide to perform arithmetic operations. They're relatively meaningless. Likert scales, Likert-type scales are a notch above that in that we can make an assumption of equal intervals under certain conditions. And we base that on simulations that we've done looking at how people respond to Likert scales. But it differs across cultures. Americans tend to interpret things in a linear fashion. So if we're faced with a Likert scale from 0 to 5 or 1 to 7, we interpret that as an equal interval scale. The distance between 3 and 4 is the same as between 6 and 7. I actually worked with a woman who was from the Navajo reservation, and she wanted to develop, we were doing an oncology study, and she wanted to measure satisfaction with the services that were being provided by our physicians. So I came up with a draft of a satisfaction survey on a 1 to 5 scale, I think, and I showed it to her, and she said immediately, this won't work. She said, we need to redo the whole thing. And I said, well, this is how we measure satisfaction. And she said, that's not how we measure satisfaction. It's 0, 1, we were satisfied or we were dissatisfied. We don't think this way. It's black and white. There is no gray. So you have to be mindful of that. But these Likert-type scales, we typically will form average scale scores by combining, i.e., adding up the answers and then dividing by the number of items on the scale. So there is some leeway there. Nominal data are those which have no quantitative attributes whatsoever. We simply use them as placekeepers or labels. Like male is 1, 2 is female, aspirin is 1, COX-2 inhibitor is 2. They're simply labels that are amenable to statistical analysis, but they have no numeric or they have no quantitative quality whatsoever. So we can measure a scale. Here is a step length measured on a ratio scale. We can measure centimeters of average step length across subjects. So 23, 24, 19, 28. We can dumb that down a little bit by selecting the shortest step length for subject C, 19 centimeters, and then measuring the difference between baseline 0 at 19 centimeters and the other measurements. So we can convert that to an interval type measurement. Or we can rank order them and convert it to an ordinal measurement, first, second, third, fourth. Or if we're interested in simply was it a long step or a short step, we can also do that. But we typically try to measure the construct of interest on the smartest scale, the smartest metric available. Then we can always dumb it down, but we can always go in this direction, but we can't go in that direction. So we always try to measure a construct again on the most sophisticated scale possible, and then we can manipulate the data if it helps for the presentation or for purposes of analyses. So any questions on that? That's very fundamental, foundational information because it determines what we can do with the data, how we present the data, how we analyze the data, what we can say about the data.
If you have any questions, hand the mic to you.
So the statistics are conventionally divided into descriptive and inferential statistics. Descriptive statistics, I'm sure you're all familiar with. We, rather than publish the data set with a manuscript, which might, it might have thousands of people in it, we try to summarize characteristics of the data by using an index of average value or central tendency, range and variability, counts, percentages, and we use these to construct graphs and charts and figures and such to visually present the data. So I want to go through each one of these quickly. Typical measures of central tendency that you will see include the mode, the median, and the mean, the average value, characterized by the mode, which is the most commonly occurring value in the data set. It might be a unimodal distribution where 2 is the most commonly occurring score, or it could be bimodal, or it could be trimodal, it could be multimodal. It's not a very sophisticated statistic, but when you have... yeah.
Would everyone who's tuned in on Zoom please mute your microphones? Some people are hearing another conversation going on. Thank you.
Yeah, so sometimes this is useful if you want to say, identify the most common hair color or the most common race/ethnicity among respondents. But it's not a very useful index beyond very basic communication, very basic information. Then we have the median, which is the midpoint of the scale. So if we rank order the scales, we can identify 4 data points above 4 and 4 data points below 4. The median for that scale is simply the midpoint. If we have an even number of subjects or data points, we take the average between the 2 middle scores. And then finally the mean, which is simply the arithmetic average of the sum of all the scores, the sum of scores divided by the count of scores. We use a number of different means. Most typically you'll see the arithmetic mean. We also I've seen the geometric mean pop up every once in a while. It's useful in reporting data that are non-normally distributed. It gives a better estimate of central tendency than does the arithmetic mean. In the harmonic mean, there are 7 or 8 different types of means that get more sophisticated, much more so than the arithmetic mean. So you want to be mindful of the type of mean that they're reporting, that authors are reporting. Measures of variability, range, interquartile range, and standard deviation are the most commonly seen or reported indices of variability. Do you know what an interquartile range is? Is that common knowledge? So you know what a range is. It's simply the maximum minus the minimum, which is a useful to describe your data set. Here in this case, we had a maximum of 96 hours, a minimum of 40 hours. The range, strictly defined, is the distance between the two. But we more formally would we probably would calculate boundaries, 39.5, since we're reporting them as whole numbers, and they could actually be, they do exist as in more detailed fashion. We probably would go from 39.5 to 96.5 and report a range of 57. But you get the idea of what a range is. The interquartile range is simply the middle half of the sample, the middle half of the distribution. So it's the data between the 75th percentile and the maximum. Well, the middle half of the distribution right here, and then, which means we have 1/4 of the distribution above the 75th percentile, 1/4 below the 25th percentile. The percentile being, in this case, it would be the score, which is about 78 hours per week. That's greater than or equal to 75% of the data in the distribution. Likewise, the 25th percentile is that score, which is at or above 25% of the data in the distribution. So the interquartile range gives us the middle half of the distribution.
I was just thinking that you would explain the graph hours per week. That might help.
Oh, yeah, okay. So these are data I collected when I worked at Maricopa Medical Center years ago. They implemented that law where residents were not allowed to work more than 80 hours per week, and it's much more complicated than that, but that's essentially the flavor of the law. So we were required at that point 4 times a year, every quarter, to pick 1 week at random and have the residents report how many hours they had worked that week. So we could flag people who were in violation. Things have become much more sophisticated now, where they're actually requiring that some residents install tracker apps on their phone so they can tell where they are at all times. I'm sorry?
I said it seems like a little invasion of privacy, just a little bit.
Well, they are indentured. So, and they agreed to do it. I work with a hospital in the Valley who is now in the process of conducting a study using that, and they selected 5 residents in general surgery, and none of them had any problems at all with it. So they're trying to, see if it works, to get a more accurate estimate of when they're on hospital grounds. So that's what that's telling us, is that 50% of the residents reported working between, say, 55 and 76 hours on that week. And there was one of them up here. This is the maximum data point where that guy is in violation. And in fact, he was called to the chair's office, and they had a discussion, because they can sanction hospitals who work their residents more than 80 hours a week. And then finally, the standard deviation, which is, I just wanted to put this calculation up here to show you how simple it is, really. So you have your set of scores. You calculate a mean value for that set of scores, And then you look at the difference between each of the scores individually. You square the deviation scores in this column, add up to 26. And then since you've squared them in this operation, once you've taken the average of 26, 26 divided by 11 minus 1, you have to then take the square root of that average, which what it amounts to is it's the average absolute deviation without regard to valence, the average absolute degree to which the scores differ from the mean value in the data set. That's all it is. Mm-hmm.
Could you make that an example of something so I understand it a little better? Like pretend those are scores for what?
You know, I don't have a clue anymore.
Well,
but
that was easy for you, but not me.
well, you could assume let's assume this is a Likert scale running from 1 to 7. So we had 2 people who scored 2 or endorsed 2, 3 people who endorsed 3, et cetera, et cetera. So what we want to know is, on average, how far did these scores deviate from the mean value, the central value of the data set? We calculated the mean right here, and then we calculated how far each of the scores differed from the mean. So 2 is 2 less than 4, 4 is the same as 4, 7 is 3 more. So if we add those up, because by definition, deviation scores sum to 0 right here, we have to address that. Otherwise, we have no information. So what we do is we square each one of the deviation scores. So that's 2 squared is 4, 3 squared is 9. You know, and you square a negative value, you get a positive value. So that allows us to sum them to 26. But what we're interested in is the average deviation. So we divide them by n minus 1 degrees of freedom, because we lose 1 degree of freedom, but it would take me 5 minutes to explain that. It's a correcting factor. We're making an estimate, so one value is fixed. So we have to remove one value from the denominator here. So we then take 26 divided by 10, and then we take the square root of that. Because we squared them at this point, we have to take the square root to convert them back to the original raw score units. So all a standard deviation is, roughly, is the average absolute deviation without regard to negative, positive.
So if I were trying to, I want to make sure I understand. So 1.6, if I'm looking at that and trying to analyze that, is that telling me that very few people deviated from?
No, you can't really, it's useful for comparative purposes. Now, if it was a very, very large data set, we have the empirical rule that tells us in a very large data set that approximately 68% of the data would fall between -1 and +1 standard deviation. But on a small sample like this, it's useful for 2 things. One, for comparing to other distributions, and second, to perform statistical tests, and I'll talk about that in a little bit. We use it to derive p-values, confidence intervals, so it's useful in that sense. Okay, so when we're reporting descriptive statistics, we tend to go back and forth between the mean and the mean/standard deviation and the median / interquartile range. For somewhat normally distributed data, we typically will report the mean and standard deviation, because the mean is a fair representation of central tendency when we have a standard normal distribution or a somewhat normally distributed data. When we have a skewed distribution, when the tail goes out to the right or to the left of the distribution, we tend to report the median and the interquartile range because they're a fair representation of central tendency and dispersion or variability. Like values of income or housing, yeah, where we have a lot of data on near the center of the distribution, but then we have people who are making professional basketball players who are making $22 million a year, houses that cost $14 million and such. In that case, we tend to shy away from the mean because it doesn't fairly, it's unduly influenced by those extreme values.
The thing I might add is that the mean is a representativeness. You know, we're trying to get some sense of what all these data look like overall. So, if the distribution is really odd, you're not getting a good idea about what the typical person is like.
Yeah, the median is much more robust to extreme scores.
How many outliers do you need in order for it no longer to be normal?
Well,
Can one just throw it off?
if it's an extreme outlier in a small data set, it could throw it off enormously. If we wanted to calculate the average or central income for a group, and we define that group as everyone in this room plus, who's the quarterback for the Patriots?
Brady.
Brady, yeah, Tom Brady, who makes what, $36 million a year or something like that. Our average income would be $14 million. So it depends upon how extreme an outlier you have. The way that we decide that empirically, there are a couple of tests here, one called the Shapiro-Wilk, another the Kolmogorov-Smirnov. Those, we can test the data set to see, it will give us a p-value, and it will tell us that these data are significantly non-normal. So if the p-value is less than 0.05, we then would probably use the median rather than the mean. And what it's suggesting is if you use the mean value, you are misrepresenting the central data point. So we usually resort to one of these two tests to tell us whether or not to report the mean standard deviation or the median interquartile range.
Now I'm hung up on standard deviation. Is a smaller one better, or does it not matter until you run additional tests?
It's almost always better because it gives you a sense of how well you've estimated the central data point. So it means a smaller standard deviation means less variability in the data, i.e. a more precise measurement. And I'll show you why that is here pretty soon. So these are descriptive statistics you'll typically see, and you can see that they're reported up here as mean plus or minus standard deviation for the continuous variables, for age and for number of teeth present, number of teeth with deep pockets, etc., the mean and the standard deviation, and then for the nominal variables such as gender, we had 68 women, which comprises 67% of our sample. So you're all familiar with these, right? You see those very commonly. Of what use is that information to us? This is from a document, a manuscript, looking at the idea that dentists should start testing their patients glycosylated hemoglobin as a screen for diabetes. Yeah, exactly. Yeah, we want to know who did they test. So the term we use is how representative was that data set? How similar is it to my patients? Could I use information in this manuscript on my patients? Could I generalize? Yeah, exactly. So why you see they had two arms here, two groups. One was basic and one was called enhanced. That was the intervention they were testing to see if they could get these guys who tested high on hemoglobin to go see their primary care doc. Of what use is information, these two columns of information? We can get a sense of their representativeness from right here, but why did they break this out into 2 columns? Yeah, and what you, I'm sorry? Yeah, so you see down here it was a randomized clinical trial, which means that they randomized patients to the 2 groups. So what you want to do is compare these 2 to see why would we want to do that.
Isn't it a better way of comparing the results of the treatment?
Yeah, yeah.
Because if you gave everybody the treatment, then what would you have to compare it to?
But what we want to know is, are people in this group similar to people in this group? And one, it tells us, did the randomization scheme work? And it obviously did. I mean, they're very close together. But what does that bias?
That they're similar?
Yeah.
So you would have, you could infer that, well, we did it to the 2 types of people and 2 same types of people, and this is what happened.
Yeah, and if they differed at the end, we could say you can't attribute it to baseline differences because they were the same at inception of the study, and now after 6 months they look different, right? So we would have to attribute the difference to the intervention because they were the same at time 1. That's all important, and we'll come back to that. So now descriptive statistics are simply used to describe a sample. That's all. These are what the people who entered my study look like. Probably at baseline, most typically at baseline. But then when we start to ask research questions, such as which lasts longer, ceramic or porcelain dental crowns, what's the best preventative intervention for childhood obesity? We don't care about which lasts longer, ceramic or porcelain crowns in our sample. What we want to say is something about the population of people who have ceramic and porcelain dental crowns, right? We want to infer from the sample to the population. Otherwise, who cares? Except for record-keeping purposes. I mean, but what we intend to do with a research question, and it only becomes research when you have an intent to generalize beyond the study sample, beyond the context of the study. Then it becomes research. So that's where inferential statistics kick in. So we have a population to whom we want to generalize. That's defined by the inclusion-exclusion criteria in our protocol. So second-year PT are males under 45 with cardiovascular disease. In order to say something about that population, we obviously can't study all second-year PT students. What we do is we pull a sample, a subgroup from that population. We might study second-year PT students at ASHES only, with the intent to say something about second-year PT students from the population, or males under 45 with cardiovascular disease in Mesa, Arizona, and say something about males under 45 with cardiovascular disease. So what we want to do is take the study sample and generalize to a much larger population. The sticking point, though, is right here. Unless it's a representative sample, our inferential statistics mean absolutely nothing, which is commonly the case in published manuscripts, unfortunately. So what if we had a population, we knew in the population cardiovascular disease was split 50-50 between males and females, but our sample is 70% female and 30% male. What could we then say about the population of people with cardiovascular disease based on our sample study, our sample-based study? Really nothing whatsoever. You can't generalize from a non-representative sample can't be interpreted in terms of a population. But unfortunately, this is very common. The disparity is not that great, but females are much, much more likely to volunteer to be in studies than are males. Yeah.
So let's say we take Ash's PT example, and let's say we wanted to generalize all of the PT program or schools, classes, I should say. But one class is not like the others. Maybe they run in a lot more women that year. Does that mean that our data wouldn't mean anything because that one year was kind of an anomaly?
Well, they're interesting descriptively, but you really can't fairly generalize beyond that sample unless they are representative on everything that might be important, breakdown of male, female, age group, background education, previous employment, everything like that. Yeah, it kind of kills the study.
I have a question.
Yeah.
This may be an ethical issue. What if you randomly threw out a percentage of them in that last example
Yeah.
so that you got 50-50?
Well, that goes back to what we were talking about way early on about survey sampling. You can weight them.
Oh, okay.
So that in that case, you would up the weight on males, decrease the weight on females, so that it would then become more representative. It's still not in a pure sense, but it'd be a corrective.
Is it a reasonable correction? It's surely.
In survey research, we do it all the time. In randomized controlled trials, never. No. So yeah, I mean, we do incorporate, we have, when we do a survey, a big survey, we will always, if we're smart, we'll always weight the responses based upon how representative the respondents are of the group to which they belong, state, sex, et cetera, et cetera.
Is that because it's just so difficult to get people to respond to surveys? So the one example that we had where she was trying to get 1,000 people.
Yeah, right.
And like, how are you going to get 1,000 people to answer your survey without any incentive? Is the weighting okay because we have to kind of?
Yeah, it's the best fix we have. Yeah, and the question though is, are those 1,000 people representative of the larger population to which she wants to generalize?
Can you generalize when you have to wait?
We do all the time. Yeah. That's where things get complicated though. I just wanted to show you this. Again, I wanted to get on to the logic, but you see here they use p-values to compare the two groups to show that none of them were below 0.05. So they can, based on that, they can say, okay, our groups were not significantly dissimilar on any of these characteristics, which may be important in determining whether or not these patients ultimately see a primary care physician in follow-up. So this is how you know table 1, this is a classic table 1, it tells you all of the variables that these investigators think are important in determining whether or not people will follow up with a visit to their primary care physician. So the key, do you know this term? Any Latin scholars in here? Ceteris paribus. What it means is all else equal. And all statistical tests are based on the unspoken assumption that all things except the intervention were equal across groups. Everything was equal across groups. And that's where many studies fail, because all things were not equal across groups. There's been a whole, the psychologists have turned the research world upside down, as well as pharmaceutical companies. I've read some really interesting articles where, just to give you one example, it was Merck, I think, bought a lot of patented orphan drugs from a bunch of other companies several years ago who had claimed these incredible results when they tested the drug in their randomized controlled trials. So Merck, of course, had to retest them to validate them. And they could replicate fewer than 50% of the results for whatever reason. What's the term? Reproducibility, what's the term that they use? Replication. Yeah. So many of the study results that you see are specific to the context of that study, and they mean nothing in the larger context, unfortunately. I don't want to get into that. So here, we use inferential statistics in a very basic sense to estimate the probability of patterns that we see in the data. For differences between groups, that what we call comparative statistics, and then relationships between variables, correlational statistics. So the problem is that clinical data are always noisy. There's no question about that. So we use inferential statistics to try to distinguish the signal in these very messy data from the noise. Do you know the notion of signal to noise ratio? It looks like this. So here, I can very clearly distinguish the signal from the background noise, the messy background noise. Here, it's much more difficult. So what inferential statistics is used for is to identify and amplify any signal that exists in the data relative to the background noise. And while I was working on this morning, Brenda Jackson brought this over to me, and she said, can you read this thing for me? I need to know those two names. And I guessed at something, but this is a perfect example. She brought it over and she said, look at this. This is noise and signal. And I could not distinguish signal from noise because it was just too cluttered with background noise. So no matter how carefully we design a study, we get variability because of how we take the measurement, natural randomness and variation in the data, in the noise, the background noise I was talking about. And then we have variation between groups. In a two-group study, we're going to have a lot of variability within patients, or across patients, even within one group, and it would look like this. I'm running out of time, so I'm hurrying things along a bit here. Sorry. So variability within, say we go back to this study we were talking about, the attempt to get patients to go see their primary care doc. Even within group who got the basic information, we're going to have a lot of variation because of differences in the patients who enrolled in the study, even within a group. So it's going to be due to genotype, sex, age, ethnicity. I could probably come up with several hundred of these things that are going to produce noise or variability in our data. So if I showed you this chart, could you tell me if these data come from one group or two groups? You can't, can you? Until I give you the background information and I tag each of the dots with a number or a designation for group assignment. And if I showed you something like that, once I've color-coded them, can you tell me, do they come from one group or two groups? Yeah. It looks like maybe two, right? They overlap a little bit right in here. So the way that we deal with that in inferential statistics is we calculate a signal. How can we distinguish the, in this case, this is the control group and a treatment group. And we're looking at change in pain report at the end of a trial. So we can calculate the variability between groups using a mean difference. So it would be 6.1 minus 4.5 would be our signal. And we can calculate noise using an estimate of the standard deviation. So what we want to do is compare signal to noise. And the way we do that is based upon the sample size and the standard deviation. We're able to model the data and guess at an optimal distribution from which these data came, based only on the standard deviation and the sample size. And it might look something like this. So then what we're interested in determining is the signal, the difference between groups. Does it stand out sufficiently relative to the background noise to make the claim that our intervention worked? Now, if I had more subjects, this is why we're always trying to get more subjects, what that's going to do is alter the theoretical distribution underlying the data right here. And you can see the difference here. I have a wide dispersion here, not so much here. So I've enhanced my signal to noise ratio. The signal is wider relative to the background noise. So we use that ratio between to within group variability to determine if the difference that we see is true or just random error, random measurement error. And the test statistic we use for these types of problems is simply the ratio of between group variability divided by within group variability, with the assumption that under the null hypothesis where there is truly no difference between groups, that the intervention made no difference, that means expectation. The expectation over the long run of this ratio, if in fact the intervention was not effective, is going to equal 1. So what we're interested in is how much does this ratio differ, how much does it exceed 1? And that's these things are calculated based, you remember in statistics, the lookup tables for the sample size and such, for the critical values. Does that ring a bell? Oh, anyway, we have these theoretical distributions, but that, again, that only works under this condition. The groups were assumed to be equal at the beginning of the study. Absent that, again, we have nothing. So we calculate the ratio of signal to noise to form the statistical test. So a small signal to noise ratio would look something like this, and it's probably due to chance. We cannot declare that to be a meaningful difference. So we have this sort of a situation where you can barely detect the signal against the background noise. Or we might have something like that, where the signal is prominent relative to the background variability. That's the logic of inferential statistics. Signal to noise ratio. Can we detect the signal relative to all the background noise going on? So we want the signal to stand out and the noise to fade. Now one way, I'll end with this slide because we're running out of time. So I was going to ask, how do we do that? Well, one way we could do that is to make the inclusion criteria very, very severe so that we have no variability across or within groups. So we could limit it only to those patients who had a genotype which has been shown to, an expression that's been shown to be correlated with pain report. We could use only females 65 to 70 years of age, only Caucasians, and only those Caucasians with the Southern European ancestry. And we'd get something like this. So we would have decreased the noise. What's the problem with this? We can only generalize to these people, right? So we might as well not do the study. So yeah, we're going to get a lot of tightly clustered data, which is going to limit our background noise. So it will be much easier to detect a difference in our signal, the difference between groups. But it's probably not worth doing with such limited constraints. So I probably should stop right there.
Thank you. Any more questions?
Okay.
So the last time we did that, we didn't want to run it because it was too broad, potentially too much variability, so don't run it. But if we make it super specific, it's also not generalizable,
Yeah.
the word. So don't run it. So when do we run it?
There's a trade-off.
Yeah.
I mean, you have to make it useful, practicable. I mean, if you're testing a drug for sale, for registration and marketing, you want to make the group as broad as you can. But you have to be in mind, you have to keep in mind that the broader you make the group, the more heterogeneous it's going to be, the larger is going to be your background noise. So it's going to be harder and harder to detect a signal. So it's a trade-off.
Okay.
You know, and they, for these trials that cost these drug companies $10 million a run, they have algorithms, simulations that they run to do that trade-off analysis. It's very, very complicated stuff.
Okay.
But yeah, it's we don't have access to those algorithms and that software, so we just have to. What we do is we will read the related previous literature to try to get a sense of what would be optimal. Of course, we don't have tens of millions of dollars at stake. Yeah.
Yeah, next week, I think.
Okay.
October 2nd.
Good. Yeah, because I'll go back over this because
Wednesday.
there's still some important stuff in here I want to talk about, and maybe we could move on to some other stuff.
Thank you, Dr. Bay.
Okay, thank you. Sorry to hurry through this. Okay. Just not enough time.
If you have any suggestions for topics or repeats
Let me see, could you close that? I've got a meeting that starts in 2 minutes. If you could close that, I'll pull this out and then abandon you. Okay, thank you. I should leave this here too.